Okay, so what we're going to do now is talk about the Linux kernel image structure, and our objective here is going to be, after we saw linker scripts in the previous meeting, and we also saw like an example of how they look like and how the kernel is made in ARM. It was not recorded, but we mentioned like how to start looking at some things, and we reasoned about what would be like the bzImage and the uncompressed image. And I also mentioned the boot p images, and so how you could like be confused if you are unaware of that and want to do kind of like forensics or things like this. So today we're going to do something that is very similar, but we're going to do it the right way. Okay, so the first topic is going to be Linux kernel image structure, and the second one is going to be how to debug the very first steps of the Linux boot up process in several variants. And the first examples will be x86, and in a later session we may do ARM. Okay. I'm just saying, if you guys sent the invitation to anyone, they must be signed in with their Google accounts, because I will not switch to accept them, and then they will not be admitted to the Hangouts, okay? Maybe I will, but I want to concentrate on delivering the talk to those who actually listen to the instructions, all right? So our objectives will be to first figure out where the linker scripts are and how they help us, and then to learn how to reconstruct. Sounds good? Hope so. All right. So let's start. I will jump from the slides to the terminal, and I will show everything like on a terminal in an organized way. If you have questions, please jump over the microphone, okay? And let's do this. So speaking of the linker scripts, we already saw linker scripts yesterday, and we saw that we have a structure that LD, the GNU linker, understands. When we look at the kernel linker scripts in the source directory of the kernel, a lot of time we will have files that actually have all kind of shortcuts. That is, instead of having like something like keep and .add.txt in all the files, if you remember, it's like keep all the sections in the object files that are prefixed with .add.txt, and make sure they are here, even if they are like not used. Then the kernel, you will a lot of times see in the linker script something like add text, and there are all kind of linker scripts and also definitions for linker scripts that are being done in the input directory of the kernel, that are going to be transformed into something where that defines our field and so on. So if you want to look how it looks like, pretty much this is like an example. It's the same file, it's broken up. Like I'm looking at the left-hand side on a file called pud compressed vmlinux.lds.source. And on the right-hand side, we have the output directory compressed vmlinux.lds, where in my kernel build, I used different directories for the input and for the output. Otherwise, you would have both in the same directory, right? So some examples of what I said right now. So here we have comments, we can ignore them. We see like output format and then config output format. So if you see something like that, you can go ahead and say, oh, so what is like my configuration? And if we go and do something like this, and I go like to kernel out, and I want to do like make menu config or whatever I choose, I can go and say, hey, what is this guy? And I see that like right now, this is like the configuration, like L32i386. In this particular case, this is the only configuration that I have. Why? Because this is the only format that the kernel supports for the 32-bit architecture. For the x86 format, I would have something else. And I could potentially, for each arc, have its own output format, but it's like a parameter, okay? It's a config parameter. Other things that we see like in the source, that we have like if defs. So we have like those nice if defs, and we have different entries. And now this is important. I told you that linker scripts are important. I can see that we have an entry point. We still don't know for what. That is called startup 32 if we are in x86 64 bits or 32 bits or startup 64 if we are in the 64-bit case. So the output for that will be whatever the configs and like the defines are, okay? Other thing that we see is, for example, that we have this guy here, head text, that I mentioned on the slide, that is translated in the output to keep add text. And we have all kind of other things. The diff here is supposed to be pretty much clear, okay? No comments, no nothing. If this is like the cache line alignment, that this is how it's going to look. If this is the page size, this is how it's going to look. And this is how the output would look like, all right? So it's very important to know that there are input and output, but the input, if you understand the language, you get like the exact picture, exactly how you want it, okay? So it's like also a matter of experience. How do we find the linker script in the kernel in order like to learn? Then essentially you can just search for everything that has LDS, and there will be additional files that are not related. And there are also some files that only end with like LD, okay? So this could be like a problem because there can be, LD is a common suffix, for example, okay? And not only like for a file type, like you could have all kind of like drivers that just have the word LD like in it. So you want to be careful about it, and you want to know more or less some things. So if you just want to, be brute and like find everything, these two ways would be like the way, and then you would want to like the second one, like without LD, and you would want to filter the noise, okay? Now, there are important headers that are used for definitions. Some would be and include some generic VM Linux LDS.h, and other could also be for architecture dependent. I have no control over these slides. I don't know why it comes and pops up all the time. I'm sorry about it. Maybe I will use this mode, but we'll see, okay? So just to show you like where some of the definitions come from, this is my output directory, okay? So it has, of course, the link. I'm repeating it for those who are like less experienced, okay? It has the link, of course, like to source. And under source, we have like the source directory. So I can see there what's going on. And again, it teaches me all kinds of things, right? Like minimal linker script, yada, 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 yada. And there I would have like the definitions. So I was not lying, okay? Like if you see anywhere something that looks like this, text main, then it would look like .txt, okay?
Can you make the text a little bigger?
Excuse me?
Can you make the font a little bigger?
Yeah, sure.
Thanks.
But I give you something that is even better, which is my expectation from everyone who like learns with me, with my courses. If I always say two things. If I say something millions of times, then it's important. Otherwise, not so much. And the other thing that I say is that if I show slides and they have path, then my expectation is to open the source and look at it while I'm talking. This is how you get like the double verification, okay? So I'm not going to talk about this one too much, but you also have like all kind of like ways to see if you have like all kind of like dead code or all kind of macros. And if or when we talk about ftrace internals, which is actually super interesting, we can understand like how exactly it's being done, and we can learn that we have actually some sections that get in for the tracing that comes like this, and so on and so forth, okay? So the idea is that an architecture can use like the generic one and can also add other linker scripts, and we already added to that, right? So why should you care? I said it several times yesterday, and I hope that it's clear and like that the motivation keeps you motivated. Let's put it this way. And there are some important examples. One, that sometimes you have no idea where something comes from. For example, like in this ftrace thing. You have no idea. Like you search all over the code, you search all over the symbols, and like, where did it come from? So sometimes it comes from linker scripts, okay? And you may want to understand why an address starts where it starts. And we'll talk about like the boot of x86. We will see this example. I'll not go over to it now. And in general, like this is one integral part of the build process and how you make your objects, okay? So just so that you see like some of the input linker scripts path, everything is going to be architecture dependent, okay? So these are like on the left-hand side. For for we have like a actually this is a double copy. I wanted to put here some ARM one, so this is never mind. It's the same thing. And we have here like on the left hand side, we'll just pick one, all kind of linker scripts. VDSO, for those who know what it is, then it's actually in user space, right? So this is used to teach and about the VDSO, the VVAR parts of the kernel ABI. It's meant to do, let's say, a simple way to put it, it's meant to do system calls without getting to kernel mode, because there is a shared page that is like exported. And talk about it another time, but I can talk about everything this time and another time. I think you already know me. So I'll try to avoid saying this. But other things that are important, except like for the VDSO, we have a real mode jump code. It's important when you have like a multi-CPUs and you need to go back from the kernel and back to the sources. And everything that has to do like with entry, that is like system calls. We have the kernel VM Linux LDS that is going to be done once we are in a protected mode and in page mode later. We have the compressed VM Linux LDS that I'm going to talk about it like quite a lot, I believe. And for x86, it's pretty much the same linker scripts, okay, for both 64-bit and 32-bit. They are separated by some ifdefs and configs that I showed you. For ARM, then we have some different scripts for some things. For example, this bootp that we saw yesterday. And the output will be like here, okay? So if you build like for a particular architecture, you can see that the file names are pretty much the same. The content is going to be different, but the VDSOs look a little bit different, all right? So for ARM, we will also have the LDSs. Now I put only ARM 32-bit. And of course, everything is very architecture dependent, configuration dependent. If you are work at some system on chip manufacturer, you get like BSP from them, then there can be additions, okay, like always. But what I'm talking now is the vanilla code from kernel.org. As I said, like in one of the first lectures. So the reason I'm showing this, guys, is that you can learn about what has been done in order to generate the output files by looking at the .cmd. It's a hidden file that starts with the same name and ends with the CMD. This is like for the output, okay? Now, how does the kernel look like? So when we go and want to boot something, actually what we gave like to QEMU in the example that I showed, we gave it the file that is under arc x86 in this image, boot, that is called bzImage, okay? And this nice file is actually the same thing as the Linux that you have like here. Like if you have VM Linux, whatever it is, let's say 415 whatever, if you check what it is, you will see, hey, it's like a Linux kernel x86 executable bzImage and all kind of parameters. And okay, now I built for 32-bit, right? But you will see the same thing here as well for this image. And this image, it actually has a structure, okay? Some very particular things are expected. On the other hand, you also have this VM Linux that everyone here, whoever debugged a kernel, I mean, something like the scheduler, something like a device driver, something like maybe the init of init main.c or something like this, that is like in the later boot phases, not what we are addressing now, then you know this is like the file that has the debugging information, right? Now, it's very, very, very important to know that even though VM Linux has, and I apologize for saying only x86 concepts, the concepts are the same in all architectures, but right now we're concentrating on x86. So ARM people or MIPS people, try to translate. I swear it's the same things and the same concepts, okay? So the bzImage, that is the big Z image as opposed to like the Z image that we saw yesterday, is actually not exactly like the VM Linux. It contains it, okay, in some way that we will see. However, and this is very, very, very important to know, VM Linux does not contain everything that bzImage says. So if you think that like the process is like this, VM Linux strip and then bzImage, you are wrong. Okay, this is not true. Okay. Now that we made this statement, let's see what is true. So I will simplify things, but what I'm saying is the big picture and a pretty accurate picture. The file that we have, like the bzImage that we're interested in, has the following things. It has a setup code that is used for very early setup, which we will see very soon. This is where the bootloader would jump to. Or if you don't have a bootloader and just want to have something like on a bootsector, like on a bootable disk, like on a something that the BIOS can jump to. I'm not talking about EFI now, because EFI has it has a different structure, but this is also the case for EFI. But the code is a little bit different. It's in the same place. You need to have some header and setup code to take care of that. So this is something that has nothing to do with the VM Linux. Then what's happening is something like this. VM Linux that we saw is going to be stripped and compressed. And to the setup code, we will actually add the compressing code and relocating code that knows how to uncompress the code, including VM Linux, but not only, okay? And it will uncompress it like by unzipping it if you use like gunzip or xz, okay? This is actually what it does. When will it do it? After taking the code and relocating it, copying to another section in memory, okay? So we have all kinds of files that we will see that are most of them are first built as ELF files, and later they are being transformed using opt copy in order to be binary files. So some of the important files, and I'll repeat it, are going to be setup.bin, that is like for the header and setup code. We're going to have vmlinux.bin that contains the things that are not the header code, okay? And an important file that is part of this one is called piggy.o that actually lets the kernel piggyback its compression, okay? So we will see all these kind of things. And the process of the generation, and I know it will not be clear to you unless you actually go and see things by yourself, but the process is like this. I'm going to show it several times, and I'm going to show it a little bit on the command line, because showing it on the command line will take quite some time, so I concentrated it here, okay? And we don't have interactive sessions, so you can pause and like look yourself. So here goes. This is the VM Linux that we have. Kernel out will be the output directory, the top of the output directory. It's an ELF. I will show later more or less the process after I show like the framework, okay? Basically, most of the object files in the kernel tree are going to be made into libraries, okay? Some of them will be thin archive, some of them will be not so thin archive. There will definitely not be any shared object, okay? No SOs. And there will be VM Linux. Now this VM Linux will be stripped. We will remove some sections from it, and it will be under boot compressed vmlinux.bin, and it will still be ELF. Then it will be compressed. So for example, I chose the xz compression, okay? So this file, vmlinux bin, is going to be compressed. Now, there will be an assembly file that is automatically generated according to some offset that is called piggy.o, and I want to show you it, okay? So I need to go to compressed. See, I made it too big so I don't see myself. Make Piggy is a user space application that generates this file And this file looks like this. It includes as a binary vmlinux.bin.xz, okay? Which is what I mentioned here. It is the output of vmlinux.bin compressed, and vmlinux.bin is taken from the kernel top directory. Now, the user space program that I said that exists, it also takes care of defining some variable. You're going to have the values z and v that I'm not going to talk about them too much, but they are also going to be generated depending on how many symbols there are, how things look like, and they are going to be represented and used in several cases. Where am I? Sorry, they're in boot. So there is v offset and there is z offset. And when we debug, you're going to see those numbers, for example, okay? For example, how long is how long is like the file, where the text starts, where like the executable code starts in some offset to something, and so on and so forth. I'm not explaining everything because it's too early for that now, okay? So we have this piggy guy, okay? Piggy.o that includes this guy, okay? VM Linux bin XZ in this particular case. So then we take this friend, this compressed one, and we link it with all kind of object files under boot compressed, okay? And we create boot compressed VM Linux. So one of the files here is going to be a linker script, vmlinux.lds, and it tells us how to link, all right? So you can have a look. We have like these sections, and it's pretty easy to look at. This is the one that I showed before. If I want to see what exactly is being done to generate this VM Linux, and pay attention, friends, this VM Linux under boot compressed is not the VM Linux under your top directory, okay? If I want to see what is the command, I can go ahead and do something like cat dot the name, like VM Linux dot cmd. And here I will see that, and I put it on the slides like in an organized way. I have a list of objects, okay, for obj and so on. This is the list. One of them is piggy, and others are all kind of things in under compressed. And piggy, I remind you, it contains all the information in the top directory VM Linux after being stripped and like compressed. So for all of this, we're going to do some checks to see that there is no need for dynamic linker here. Otherwise, we fail it. And look, do you see this guy, -t? It's from our linker 101 presentation, right? So we give our linker script. There will not be a LD default script or something like that. So we take this and we add to it a kernel info. We add to it a file called add32.o, and we essentially add all these kind of files that are here, okay? That most of them are also there, including piggy. This is what we do. This is our command, okay? After we looked at the files. So this is the next VM Linux that we have. Now, and I made a lot of effort to put these colors. So if you don't like the colors, it's your problem. As long as you remember them, everything is good, okay? They stand out, and I really hope I checked it. I mean, I did not like make mistakes in them. In the next slide. So like, for example, the compression, how VM Linux like XZ was done is listed here, okay, in my comments. And it also created GZ. It could also create other formats. Now, this guy here is going to be stripped. And how do I know all these things? First of all, because I know the kernel build system. And second of all, because I can look at the commands for example, under boot.vmlinux.bin.compressed, okay? So what's happening is that this guy, VM Linux, is going to be stripped again and removed of kind of sections, and then we transform it to binary. And this is the next step. So just to prove what I just said, if I cut VM Linux bin command, exactly what I say, obj copy, -o binary, remove section note, remove section comment, and what is the source, VM Linux, We strip it. What do we strip? VM Linux. And what we have here is the output. All right. So I was not lying. And now all this had to do with some code that we may know, for example, the init or the scheduler or the tracing or a memory management or a lot of other things. But then there is another part. And this part is this one, the header and setup code that we're going to tackle now. So what we have here is this. Under boot, we have setup.elf and we have setup.bin. Now, setup.elf, you can see it's an elf file, and setup.bin, you can see it's an x86 boot executable bzImage that, if you remember, when I looked at the bzImage, for example, at VM Linux, if it was here, yeah, for example, at this, I see there that it is a x86 boot executable, okay? And also here, they call it bzImage. I mean, this is how file recognizes it. Why does it recognize it like this? So just like in any file format, we can go and like do an X dump, okay? And we'll see that both of them start in the same way. I didn't want to do it like this. We can see that both of them will start in the very same way, okay? Now we see here those strings, but the strings are not the thing that is important. There are going to be headers. There are going to be well-known headers also, like for the compression, that are like inside some of, like, you know, the bigger kernel code. There are going to be magic numbers in all kind of well-known places, and file know to interpret them. Okay, so we have this setup, and what I mentioned is that setup.elf is an elf, setup.bin is a binary file, and it is going to be contained exactly as is in bzImage. If you look at the first bytes, it's going to be exactly the same. Only reason why it wouldn't be the same is if something called the boot protocol changes, and if the header changes, which is very, very, very unlikely. Okay? Now, what is this? So first of all, I can prove again that setup.bin is setup.elf only made binary. That is, we get rid of everything that we like. Okay, so if we look at setup.elf, we get rid of like the head, the elf header, we get rid of the tables, we get rid of all the sections, we get rid of everything, and the only thing that we leave is the bytes themselves. Okay, so it means that if I write such a binary code, I need to be aware of the relative addresses, or if I want to be like a position independent, or the non-relative addresses, if I know where I'm loaded, like I need to be aware of that and program according to this. Okay, so that's how things work. So now this guy, as I told you, setup elf becomes setup.bin, and bzImage is the combination of VM Linux bin that we saw before and of setup.bin. Now, what is this setup.elf? So it was made out of files in the boot directory, x86 boot. So the one who decides how to put it has a different name in this case. It is setup.ld, not lds.s. Oops, I'm in the output directory. Yeah, because this is in the input directory. Do not generate another file out of it. So let's have a look at the input directory. And I will go to arc x86 boot, and here I will have a setup.ld that doesn't use any of like the special keywords. Okay, it looks exactly like what I taught you yesterday. Like we have, this is LD language, end of story. So it has output format, output arc, entry, and so on. Now, what did I tell you yesterday about like the entry point? The entry point is important only if somebody cares about it, okay? And when it's, what does entry do? Entry say, hey, this address will go into the elf header, and we say you start from here. But if I strip it and it's not an elf header, then I don't even care about it, okay? But I do start creating it in this way. Now, speaking of the header, we have here some things that are quite interesting because we decide some addresses where they will start. For example, PS text starts right here at 0. And we decide, for example, that one particular address where header is, we don't know what header is yet, is 495. Okay? So we have this, we have all kind of alignments, and we have something, you will know why I'm emphasizing it. Not that it's that critical, but we'll see it in the code, and it's like a reference point. When you want to learn something and we have no idea, we are looking for reference points, right? We're looking for friends. When you get in jail, you want to find a friend, right? So we have all these things, okay? So look at this, familiarize yourself like with this number, okay? With the signature. And we also have this thing like some asserts. So if like a variable that is called header is not in the position 1F1, which is 497, okay? We know that the setup header has the wrong offset and so on. Goes to 495, okay? Now, this is like the linker scripts. Now, how was setup generated? I'm looking for setup elf because bin was stripped of it. So here we can see that we use LD with the linker script that we gave it, okay? It's an elf i36 architecture, just like we did yesterday. And we have all those nice files here, all right? Okay. So we know how this works. And this is great. Okay? And we will get back to it very soon. So just to keep those things organized, I will present it like in from another perspective. And this perspective is actually this one. I recompiled like what I'm presenting now in a different directory, okay? And I use the same configuration file, okay? And when I build it, I have the build output. Now, I'm 1000% sure that some of you never even saw it in their own eyes. Some of you never bothered to look at everything. And you have no reason to. And if it's interesting, I will give a different talk about it at some other time. But what I want you to concentrate is this. Like when we build, we have all kind of like targets that are happening and like steps that are happening. For example, we have here parsing, okay? For example, we have here things that have to do with tools on the host. We have here generation of the system call tables. We have generation of the makefile. We have all kind of wrappers. We have AS means assembling. IR means that we're archiving, that we're creating a directory, a library, sorry, called built-in.c. And CC, of course, means that we are compiling, right? This is for the signatures, I think, yeah. So from kernel 4 dot something, if you don't have like a libSSL, this would fail otherwise, okay? We include certificates, we'll do all kind of things. And this is like the build log, okay? But what I show you now is the end. So the end of it is going to be this. We're going to take all kind of library and want to link them into VM Linux in top directory. And this VM Linux, it will actually be generated of multiple paths of the objects that we have plus symbols, okay? So when you see modules, if they're built in, it means that this goes into the kernel, not loadable kernel modules. Now I don't even support loadable kernel modules in my build. That's why I have like mode post, 0 modules. But the combination of them is going to end up in the VM Linux file, okay? Which is linked here. LD is a linking target, all right? Now, here we create a system.map. We have SLR, then we need to know like the difference, but never mind, we'll not have the SLR now. And here we have things under boot and under boot compressed and bzImage. But it will be easier to show it like this, so that's what I'm doing, all right? So this is like the end of the steps of the kernel VM Linux. It's also like in the same colors. And what we will have now on the left-hand side is the files from boot. We already saw how to do it. They will create setup.elf that will later be setup.bin. So we see now that there is ld setup elf and opt copy to setup bin, and build, which is another like building script, build like the bzImage and combines both of them and puts also some offset and CRCs, all right? And in the middle part, we see the creation of the linker script. LDS means creation of the output directory linker script from the input directory linker script that has almost the same path with the dot capital S at the end. We have here assembly. We have the generation of v offset and z offset files, as I mentioned before. We have here, the offset is actually in the next page. We have here compiling of some things. And we have obj copy for vmlinux.bin, we create it. And we have compression of VM Linux, xzkern, otherwise it would be like gzkern. And we have make pg, and we have assembling of the resulting S files, and we have LE to the VM Linux, okay? So that's like what the phases that we have. I mean, there is no voodoo, there is no magic, and this I already showed you. Everything looks the same, okay? So at the end, we have our images, and since I proved to you that the images have setup.bin just as is in the beginning of the file, we can go ahead and look at it, okay? So the functionality that it has, it will run on real mode, and it is the first instructions. If you look at the file as it is, it's going to have some things that have to do with actually being called not by the bootloader, but by being run from a boot sector. So the label underscore start that was linked doesn't necessarily align with reality. And this way or another, whoever runs us, it is the bootloader that runs us, or like QEMU with the dash kernel that implements the bootloader, needs to know what address interests it, okay? It's very, very, very important. So whatever is happening on setup.bin does not even enable paging, so I cannot use debugging methods that I'm expecting, okay? Before we go into the debugging, I just want to show you a little bit about like the difference, how files look when they are structured and not structured. So this is the same file of setup.bin and of arc-setup.elf, okay? And I enabled myself to disassemble. So we see here some instructions, all right? Now, we see several. Here we have one particular section, and then we have .text32 section, never mind exactly what. And the colors match to the bytes. So if you are very careful or very fast reader, you can see that it's the same content. So what we actually have is like everything on top of the other, one on top of the other. Okay? So what it exactly does, the code, it doesn't really matter. So this is what we're going to tackle next, like the setup. And as I mentioned before, there are additional files. And a very, very, very important one is going to be the compressed VM Linux. That one of the things that it's going to be doing after some jump from the setup code that I will show is to run in protected mode. Protected mode, especially for the ARM people, it does not yet mean that we have paging enabled, okay? So we don't turn on like the MMU and take care of like a paging. And for x86, it doesn't mean yet that we have paging enabled. We did not set the corresponding bit in the corresponding control register yet in this page. But it is another mode that is like not real mode, and it runs on 32-bit. And you can use the segments if you know x86 architecture, but you don't have to. Okay, so we'll cover it also, but this will take like some time to get to. So I can make it like very fast. I can make it like very slow. We'll see how we go. Okay, I'll try to keep the recording short, but it's like a type of subject that you don't do like in 10 minutes unless you just show, hey, these are the phases. Thank you, goodbye. So we'll start with setup. Okay, and any questions so far? Okay. So what we did now, we actually observed like where we put different linker scripts. We learn about the structure, and we learn how we can actually use some information, how files are built, learning the build system, how to look like at the command builds, and so on. So now that we understand it, and that I gave you like the introduction of what is going to happen, like the setup code, that is just going to be run as is, let's see how exactly it's run. Okay? So we're going to do two things here. We're going to learn how to single step the kernel, but in order to do, and we're going to do it either by being run from a bootsector or by being run like in the normal way with the bootloader. Now, why do I say it like this? Because first of all, in the past, you were supposed and you could run the Linux directly from bootsector. Now, as you will see very soon, then it is going to tell you, please use a bootloader, as you saw in the text before if you were alerted enough. However, there is a very nice thing about the way of reproducing and debugging it, because you don't need to reboot things all the time yourself if you don't get the addresses right, which is something very, very, very important if you have no idea what you're doing. Okay, and even if you do, so we're going to do this. Okay, so the strategy is going to be as follows. To run from a boot sector, pay attention to this. I'm going to be using QEMU. By the way, it is important if you use the x64 or the i386 one, according to the architecture. And one of the things that is a little bit harder to grasp sometimes, and too bad like I didn't connect the camera so you can see the expression on my face, is that GDB and QEMU behave differently in their combination together in different versions of them. Okay, so if you want like, you know, a one solution for everything, and you're not like, you don't really understand how I like to work with the combination of them, then you are expected to be disappointed. Okay, so I'm going to save you some disappointment by giving you some tips and from experience. So the way we're going to go is as follows. First of all, pay attention. Usually when I boot QEMU, I give it a dash kernel parameter, or I give it like an image or something like this, like an ISO image or whatever, or a hard drive or so on. And the hard drive would usually have like grub or another bootloader on it. Here, I do not give it the dash kernel parameter. Okay, like the way things are supposed to be done usually, I would go and run QEMU system whatever dash kernel blah 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 blah. Okay, dash append if I want, all kind of things. I'm not doing this. Now I'm running without the dash kernel, and now there's no need for append. This will say that, hey, this is like my disk, so this is my boot sector. Okay, dash s and dash s mean stop at the first instruction of QEMU and open a port so that you can connect to it with the remote debugger, which is what we're going to do. We're going to connect to a local TCP port of 1234. This is the default. You can also provide it instead of S with the dash GDB, TCP, and your port, okay? Now, very, very important thing, super important thing. You must use, at least for the first time something breaks. I mean, not break like not working, but breakpoint, hardware breakpoint. And this can cause you very annoying problems and can cause you want to jump off a very, very tall building because there are some well-known bugs in QEMU that sometimes after breakpoint, you cannot single step or you cannot continue. So you might want to like do a loop or something like this and not even sure if like the loop progressed or GDB just stopped like working, okay? So you need to be aware of these things when you want to do things. Now, other things about the way the code works. For those of you who never debugged anything in GDB, for example, I think I made some application yesterday. Yeah, let's go. And I want to debug like a low C. Okay? Then usually, this even have main. Wow, I have an address. Everything is great. Usually, if I want to put a breakpoint someplace, I could just go ahead and put the address, and that's it. Like I'm going to go and I'm going to put a breakpoint at the particular address. Star is very important. And I'm going to run and I'll be happy. I can look at the registers and everything is great. I have all kinds of registers that you would never care about in x86. In ARM, of course, you would not care because they don't exist. And you would care about them maybe if you compile something like with canaries or with all kinds of things, and then you will see like GS at the place of 14 and stuff like that, okay? But you would never even care about them. Why? Because they're not important. They can be used, but they're not important for what is called protected mode or long mode in x86 64. However, they are super important in 16-bit real mode. Super important. Very, 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 very important. Why? Because the program counter on whatever you have is not going to be enough for itself. To represent an address, you need to have a segment also. This is also true for the stack pointer, and this is also true for a data pointer. So every address that you see while you're in this thing that is called real mode, which is how the computer starts, is going to be in this addressing scheme. So you would want to multiply it by 16 and then add to it, multiply, I mean, the corresponding segment by 16 and then add the address. So for example, if I want to put a breakpoint on the address 210, and this is something that is a little bit weird, but it's true. I mean, this is for this assembly. The program counter there is expected to be 0. Then it means that the code segment would be x1020 multiplied by 16. So we add another 0. Okay? That's how things work in this real mode. Now, there are some definitions on where I am, like what is this segment. What we'll care about mostly now is going to be the code segment. So there can be, unless I do something that is called long jump, then the code segment will always be the same unless I push something to the stack and did a return and popped from it, which is something I can also do, okay? If I pop like into like the code segment or pop like into the data segment and stuff like that. Now, I'm being like slow because explaining segmentation mode is not something for 5 minutes or 10 minutes, but ignoring its existence is unacceptable because you will not be able to understand anything. So for the sake of you who have absolutely no idea what I'm doing here, when I'll start showing things, then you will understand at least why I mentioned it. And for all of you who know, yeah, of course I wasn't very orthodox and I didn't give the entire picture, okay? So the important thing is that, like, unless when I have jumps or branch or calls, then unless I do like a long jump, I'm going to still be in the same segment unless I modify the segment like in a particular way. So when I start work, if I boot directly from a boot sector, then the BIOS will work on a boot segment. The first segment, the code segment, will be x7c0, which means that if the program counter that I'm expecting to start with is 0 of the very first instruction, then I would like to start at address 7000c0. Okay, 7000c100. Okay. All right. I hope this is clear. And there are all kind of definitions in the code that have to do with segments, but we'll not deal with them now. Okay, the kernel has its uses for that. So we're going to get and see things very, very, very fast. But first, I want you to be aware because you will see it. Whether you see like the slides and we go over them, or whether you go and experiment yourself, you will see it. Let's say that I put a breakpoint, okay, in a particular place. Then sometimes things will not look exactly as I expect because there are some places where the segments don't make sense or like a little bit weird. And so when you work with GDB, then at least current versions, if you give like the entire addresses for the breakpoint, then it's okay. You just need to know what is like the combination of the address and you'll be okay. For older versions or for some versions, sometimes you need to be very particular and like break on the program counter. So things change and you need like to see what is like the tool that you have at hand. And when they're buggy, it's annoying and problematic. Other things with GDB. No matter what you do, at least not in the versions that I know, the moment you have segmentations, if you disassemble or try to look at the program counter without multiplying in the code segment, you will see the wrong things. Okay? So it's very important. This is why I repeated it now like 11 times. Now the other problem is that sometimes GDB doesn't understand well the code. Remember that I showed you the signature in the linker script? Then somewhere, and we're going to see it, there is a place where we actually compare some place in the memory, 36b8, to this 32-bit integer. However, sometimes you will see completely wrong instructions. And if one instruction is disassembled in the wrong way by GDB, then the next instruction is going to be disassembled in the wrong way. So if you just see this, you may not know what you're doing. And then you just have to go and see what are the bytes itself, go to the manual, and disassemble it in your brain, okay? This also applies to ARM. It super applies to ARM because sometimes there are different like architectures in ARM and there are differences. And sometimes like the maintainer of the tool missed some instruction set, missed some opcode, missed something, okay? And when it shows, hey, bad, I don't know what I'm doing, then it's one thing because you know that it doesn't know what you're doing, what it's doing. However, when it shows something that is a legit command, then you need to start and see what's going on. It also happens with register names sometimes. These kind of things happen, okay? So when we debug, some important things. Reason why I mentioned like objects and linkers and stuff like that is to help you to not just see addresses, but rather also see function names sometimes. And for this, you need the symbol file. Now, symbol file will be sometimes used in order to reset all previous information because the way to add new symbols, which is add symbol files that get start of text, the first argument is where you have the .text section. And if you don't have a .text section and you don't care about it, just give it any number. And for other sections, you're going to have -s, the section name, for example, .header, and space the address. So you can put it, this is optional, you can put it for each section, okay? So for example, if I add this symbol file, arc x86 boot setup.elf, as my symbols, then I need to know where the sections that I had reside in memory, okay? Otherwise, I will see wrong addresses, even if I provided a symbol file. So we're going to do, when we debug, we're going to, every time we know that the files that we need, like setup.elf doesn't contain other code from like after we are already like in paged mode. So we're going to switch a file, okay? And if we want to go ahead and see what's happening after we are like in a page mode, we're going to switch a file and so on, okay? So you need to be aware that if you want to help some support and not just look at disassembly without any symbol whatsoever, then you need to know what object files you need and where to put them in memory. Deliberately, I didn't give here addresses because they change. Okay? So having said that, we can now start. Okay, I told you that the first section is going to be at 0x7c100, correct? So we're going to now go ahead and debug this. Fair enough? Now, let's have a look at the files and where we start. So the file that I'm going to be using now, which is this one, I'm going to go and disassemble it as we go. If I run with QEMU, I'm going to run without the kernel param, as I told you. Okay? And I first want to show you what it is that we are running, okay, without debugging. So let's do this. So if this is like my output, I'm going to do QEMU system 386 dash kernel. Sorry, without dash kernel. Boot arc x86 boot bzImage. And do you see this? If it's small, I apologize. I don't think I have a way to control it. Okay, maybe I do, but it will be with ugly resolution. I want to take a second and look at it. Booting from hard disk, use the bootloader, remove disk and press any key to reboot. If I go and press any key, again. If I press any key, again. So at the top, you can see the BIOS print, and then we see booting from hard disk, use the bootloader again and again and again and again and again. Now, if you looked, and I showed it like in the slide, actually, but if you look at the file, let's see, under boot, header.s, which is the file that we're now debugging, then you will see these messages. Use a bootloader, remove disk, and press any key to reboot, okay? When we looked at VM Linux and saw how it looks like, we also saw this text. So let me go to the output directory just to show it. And I'll go here to arc x86 boot. And I will do, for example, head to setup.bin. Remove disk and press any key to reboot, okay? Same thing as if I go and do head to bzImage, okay? What you also see when I do head is this is my panic and this green thing. Welcome to run demonstration. Boot header S says hi. But this is later on. You also see no setup signature. You can see these things. It's the same thing, all right? And it's green because my terminal supports parsing colors. Was there a question or somebody trying to join? I will not answer questions unless, Yuval, I will not answer any question unless you guys jump over the microphone, okay? So the question is, why did you treat VM Linux as a symbol file? First of all, it includes files, but there are several VM Linux. And I gave an example on how to add it when you, I gave an example on how to add it when you want to debug. So when you want to have simple information, but we'll get to that, okay? You first need to see like how things look when you don't have any simple information. So this was like an example, okay? And I treated it like this because it is a simple file. So this is how things look like, and this is where it came from. Now, how do we boot? What is going on? So let's have a look at the following scenario, okay? So I will go, and I really hope I'm in the right terminal. I already happened to many of them, and run this thing. Debug boot sector. That it's the non-commented one here, okay? I enable KVM because it's faster. I don't even need it, okay? So this is what I'm going to run. Fair enough? So here I'm going to do this, debug boot sector, and it will wait, okay? On another window, I'll go to the output directory. On another window, I will debug, okay? And let's do it like this. And at first, I will just open GDB. I'll set architecture to i8086. It doesn't mean it will be perfect, but it will be at least be something. And I will do target remote 1234. So what I have here, I didn't even specify like a symbol or something like this. It's okay. What I have here is this. Address FFF0. And if I look at the registers, I can see that we have CS of F00000, okay? And instruction pointer of FFF0. This is why GDB thinks this is the address. Now, if I really want to see what is the address in memory that I'm being looking at, then what I need to do is, and this is examining like memory, I will need to do 16 times the value of CS plus PC. Okay? So what is the command that I have here? A long jump. Okay? To the segment S3630, and this is the address. If I looked without the program counter, without this, then this is what I see. ADLEAX, which is, anybody want to guess? Let's see. As X, all zeros. Okay? So many times when I do these things, like things, okay, don't make sense. So now, like if I want to go until the next breakpoint and I don't have a breakpoint, I'm going to do count. Now, why did I say that this is a good strategy, even if this nobody uses without boot sectors? As you can see, booting from hard disk use a bootloader. I mean, without bootloader, because I can now go ahead and continue running. And if I had a breakpoint and I overstepped it, I could run again. But now I'll just do an interrupt, and now we can see that when I do interrupt, QEMU is still executing, okay? I am somewhere, I'm doing something. Maybe I'm lucky enough to be in the kernel code, but you need to be super lucky, okay? Like, you need to be unbelievably lucky enough and to do it fast enough. So now I'm stuck, I can't reboot, but now I'm going to go ahead and reboot. And then I'm back in business and so on and so forth. But I'm going to do something else. What I want to do, and I put it like on the right-hand side, okay? What I want to do is look at the header.s to disassemble these friends, okay? And I know that the boot segment is 0760, 07C0, okay? So I'm going to try and put a breakpoint in this times 10. And it must be a hardware breakpoint. So I'm going to do a hardware breakpoint, x70 C0, and I multiply it. So now I put hardware assisted breakpoint at 1. Okay? And I will continue. Now I'm going to press enter. And boom. Breakpoint 1 at blah, 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 blah. Now I want you to look at this very carefully. First of all, look at the left-hand side. We have like bootsector. We have if config stub exists, then we have here a header. That means the PE header, MZ. Okay? It's not. So the first instructions that I'm expecting to see if I examine the memory are these guys. Long jump to bootsec start 2. And after that, I will see move W and so on and so forth. So let's put a display point. By the way, if there is a request, I will do like a different session about like explaining some GDB, how to like work with GDB, but I don't have the luxury to explain every command now. Okay, so ask me later perhaps, because otherwise it will be forever. So I'm going to display now. I'll say every time you stop, and there are nicer ways to do it, like with setting command stops, setting stops, and stuff like that. But I'm going to do it the simplest possible so that if you don't feel comfortable with GDB, you will have less questions. I'm going to display 20 instructions from I'm doing it on purpose, the current program counter. So this is what I see. L jump, C8C, and X7C0005. And later what I see is move CSAX and move EAXDS and all these kind of things. So these things, what I see, like the instructions that I see after that, they look a little bit different actually. Okay, so something here looks not completely wrong, but it also doesn't look exactly right. And where did they get like these addresses from? So what would happen? Let's see at the registers that we have. The register that we have right now are instruction pointer is C00, and the code segment is 0. Okay, what happens if I go ahead and do a step instruction here? So I stepped instruction, and now what I see is that the program counter is 5. Okay, and we see lock ret. Why would we lock? What does it have? What lock ret? What's happening here? This is a lock prefix, but lock prefix on a ret. And what is this loop? And what's going on here? So let's have a look. Instruction, the code segment is 7C0, and the program counter is 5 as I expected. So I'm going to fix this display error. And as I said before, sometimes there will be misinterpretation of commands regardless, even if like the program counter and code segment are right. Undisplay removes all the display points. Display starts or shows things when I stop. And now I'm going to do the same display command, but I will add to it 16 times $CS. And look what we have. Now this is the real program counter, and we have move CSAX, okay, AXDS, and so on. So you see this guy on the left-hand side? Same code. So look what we do here. We do all kind of registers, and we move. We set interrupts, we clear direction flag, never mind what they are, and we move the address of bugger off message into the source index, which is a register. What is bugger off message? It's this. Use a bootloader, remove disk, and press any key to reboot. Okay. So if I now go in single step, every time a single step, then because I did display, I will still see all the rest of the instructions. Okay. So I single step, I single step, I single step, single step, single step, single step. and I see that I moved this into ESI, and I can now go ahead. First of all, maybe this command was not interpreted well. Maybe it was. Let's see. We can double check some things, okay? So I can see that ESI here is 2D. So what's happened here? Like, what is going on here? Why? So there are all kind of things that we need like to figure out, like what is going on. I mean, what is this an address? Is this a mistake? So some things are just wrong, okay? But if I now go ahead and look, for example, at ESI, and this is important for real mode, sorry, $X ESI, I will see something. So ESI points to address 2D, and this is like some content. Does it look like a message to us? Let's look at more things, like x/20x ESI. Looks like a bunch of addresses, or does it? What is it? If it was a string, I could just go and look at it like this. But this doesn't look right. Now, what is the thing? I'm pointing to something that's supposed to be data. And if I look at the segments, I also have this fellow here, okay? So what I would want to do is, instead of looking at ESI, I will be looking at ESI plus 16 times DS. And the same thing applies for stack and so on and so forth. So this is the real address, okay? So the takeaways from here is that you can't trust GDB and you need to know what you're doing. So having displayed that and having said that, when I do this by C thing, let's go and see what are the instructions that we have, okay? So the next one is going to be in 7C14. And the question is, okay, so what is 7C14? What is this? Is it even the right instruction? What was the previous instruction? Where was this CLD? Where was this move to ESI? Was it moved to ESI? So let's see what's happening. So we have it here, CLD, that was right here. And we have move W, and then we have indeed load SB, okay? So back to the debugging window, we have this thing, after we have end of AL, and then we have jump 0, that is if AL equals itself, then we have jump 0, BS die. So look at this. This is an end if AL, which is a single byte, is null. So what's going to happen in message loop is that we're going to do everything here and then jump back to the beginning. And when we reach a null character in the address that we saw here, we are going to go and jump to die that does this. So what do we do here? We do the following. We have and if it's not 0, then if it's 0, then we jump. If it's not 0, we move a value to AH register. We move a value to BX register, and we call it 0x10. AH is the higher part of the AX register. AL is the byte that we're currently at. And X10 is the BIOS service routine in x86 that shows something, shows a byte to the string, to the screen. So every time we're going to do this, and now I'm going to take the courtesy of printing, putting a breakpoint at the end of it. So I need to see where is this address. So I see some jump here after the 010. And I'm going to figure out what it is. So I'm going to put a breakpoint, for example, here, okay? I'm going to put a breakpoint here. And I'll show you like how things look like on the screen, okay? And I'm going to do the count. Look at the left side. You see U. And now I printed one thing, but then it got stuck. Why it got stuck? because of bugs, of annoying bugs in QEMU. Okay, so I will most likely need like to remove it or remove all of them and so on and so forth. I can go ahead and do some tricks and do like temporary a breakpoint and then continue, but it still does not continue. So I need to like delete everything. And now if I step instruction, then it works. And then I will do like a temporary breakpoint and continue. Now you see the S, okay? And now I can see what is the status of the breakpoint. And it is currently deleted. Can I still single step? No. So I need to delete it completely and so on and so forth, okay? So there are some annoying things here. All right? Just so that you see, like I will now, I can go ahead and put a breakpoint in the loop in another place. Like I'm going to put it after the, so we had like this nice code here. And I'm going to put, let's step instructions. I'm going to put it here, okay? So where I check what is AL, and then I have jump E to 0x7c22. So I'm going to put a breakpoint here, and then I expect all the messages like to already be printed for me, which is exactly what I see now. And now 16 is an interrupt that gets input from a user, but I no longer care about it, and I can go and proceed here, okay? Questions so far? So this, in fact, debugs shows how to debug the first part, which is the boot sector code, okay? Any questions? Good. So what we're going to do now, I'm going to stop the recording. We're going to take a quick break. And after the break, I will show you how to actually do something that are more interesting. After we gain like initial debugging experience and so some of the challenges, how to work through the way until we get to Act 2 init actually. Sounds good?
Yep.
So let's take a quick break. And this is the end of this recording. Part 2 will be very soon.